Binary search. It's a computer science term that when you first hear it, it sounds complex and super intimidating, but actually once you understand how it works and understand the concept, it's super simple. My hope is that by the end of this video, you'll have at least a big picture idea of how binary search works. We'll even throw in some code examples as well using vanilla JavaScript. This is Don Juan Codes. Let's get started. Okay, so in my last video, I coded a square root algorithm, and apparently, come to find out after the fact, I didn't realize it at the time, but apparently I'd used a binary search algorithm to figure that out. I was looking at a lot of posts on Stack Overflow, looking at other examples of how other people implemented the same thing, and I saw the term binary search a lot. I was like, what the heck does that mean? Binary search. It seemed intimidating, but once I understood the concept, everything kind of fell into place and made perfect sense. So the term binary means two parts, 0 or 1, and basically you take your search area and you divide it in half each time, and that's exactly what I did with the square root algorithm, and it worked out really, really well. So yeah, I stumbled upon this concept that was new to me. I know it's probably not new to a lot of other people, but you learn something new every day, so I thought it was kind of interesting. So yeah, let's look at a brief summary of what binary search is and how it works. All right, so what is binary search? So binary search is just, another search algorithm, and the way that it works is that it divides the search area into halves. And so this pattern continues, it cuts the area in half, looking at the term in the middle until it finds a match. So one common use case for this that I heard of was if you have a catalog of stars, there's like millions or even billions of stars out there, and if you're trying to find one, binary search is actually a very efficient way. It's surprisingly efficient to find the match very, very quickly. So let's say that you have, let's pretend that this rectangle is the entire set of known stars, and then we're going to divide it in half again, and again, and again, and again, and again, until you find your match. So this algorithm is very, very efficient because we're discarding half each time. And the cool thing about this is that the search area decreases logarithmically. So a logarithmic curve, as you can see, the red line here is a logarithmic curve, and it basically plummets towards 0, whereas the blue line is a linear curve, and that continues in just a straight line very slowly down to 0. Now this is the maximum number of possible iterations. So for the linear search for a set of 100, you'd have 100 max iterations for the worst case scenario, the worst efficiency. And for binary search, the worst possible scenario would be 7 max iterations. And even more pronounced, if you have a set of 1,000, binary search is going to take only 10 iterations, whereas linear search is hardly even moving at this point. We went up to a max of 20 here, and the blue line is barely moving. So hopefully this demonstrates that in an ideal situation, binary search is going to be very efficient. Some common use cases, like list of students. If you're looking at an alphabetized list of grades, for example, humans actually kind of do this already by instinct. If you have a stack of papers of students and they're all alphabetized, and you are looking for Zane, for example, you're gonna flip towards the back. If you're looking for Stuart, you can flip halfway, and then if you land on Mike, you're gonna discard the upper half because that Stuart is farther down the list than Mike. So that Stuart exists somewhere in the back half of that list of grades. Hospital records, sign-up sheets for marathon runners. Lots of examples, use cases for this kind of search algorithm. Now, there's one big caveat, and that is that binary search really only works if the list is sorted. So this actually is a big problem because oftentimes simply sorting the list is going to be very time consuming in and of itself. And if we have to sort the thing ahead of time, if it's not already sorted, then you kind of lose all the benefit of binary search. So that's binary search in a nutshell. I'm going to include some links down in the description if you want to dive deeper into this. But I was actually interested in coding my own version of this using vanilla JavaScript. So let's get into some actual code examples. Okay, here is our finished product for binary search. All right, so let's walk through this. So here's the function search binarily, but the crux of the algorithm is down here. I'll explain this in 1 second. So on the right-hand side, here's our log, our printout of what's happening. So first, we are looking for the number 3. Here's our original array. And as you can see on the first pass, it eliminates the top half of the array. We're left with this. And on the second pass, it eliminates this top half, actually more than half the top 3 items, left with 3 and 7. And then it finds 3 after 3 passes. It does this for pretty much any search term. Looking for 7, it finds 7 after 2 passes, finds 12 after 1 pass because it's closer to the center. So yeah, I got this working finally. I'll kind of try to walk through how this works. So our function takes a target, we pass in our set, basically our haystack of what to search in. The target's what to search for, the set is what to search in. And then we pass a custom checker function for checking our match. The first thing that we do here is we do sort. So again, we lose our efficiency by sorting, but you know, this is just for demonstration purposes, just for fun mainly. Now this is the algorithm, the meat of it right here. So the next index, given a min and a max, we return the max minus min divided by 2. So that's going to give us the halfway point. Actually, plus min is our offset. So what this is basically doing is it's giving us the center point between max and min, and then it's offsetting that by the min. Hopefully that makes sense. And then math.floor ensures that we have an integer because obviously you can't have a decimal value for an array index. And this current index is what we're going to use. As you can see, we're immediately invoking the next index function with limit down and limit up. Limit up, when we start our first pass, is just going to be whatever the length of the array is for the set sorted. Now we have our loop here. By the way, this I here is only a safety check to make sure that we don't have an infinite loop. Good practice that I usually try to do whenever using while loops, because you never know, you always do something. I seem to do something stupid very often with while loops, and end it with an infinite loop. So first we check to see if we have a match for the current index, and then we check to make sure that limit up minus limit down is greater than 1, because if this is not true, then that means that we're left with either a single item in our array, or we're left with the 0 items in our array. In either case, we either have a match or we don't have a match. And then we make sure that we don't run into an infinite loop. So then we calculate the limit down. Basically, if the thing that we're searching for is less than the whatever the current value is, then we want our lower limit to stay the same. But if the target is higher, then we want to, chop off our lower limit at the current index. So similarly, if the target is greater than the current value, we want to set limit up. We don't want to change limit up. But if the target is less than, so for example here in this case, looking for 3, the first thing it searches for is like, I think 63 or 45, I forget exactly, probably 45. So then it's gonna change the limit up so that the top half of this thing is discarded. And then we update our current index by calling next index with whatever the value for limit down and limit up are. So yeah, that's the algorithm in a nutshell. And then this on return function is all it's doing is just giving us a visibility, giving us the opportunity to log out the number of passes and whether we found our match or not. So that's just a convenience method for giving us visibility as to what's happening. But yeah, that's the algorithm in a nutshell. That's how it works. This also works for strings as well as numbers. So as you can see here, I have an unsorted array of animal strings, and the first thing that it does again is to sort the array in the algorithm. And so like looking for goats, we have our array of animals. It eliminates half of those results. And then it found a goat after 2 passes. Looking for dog, we have our original array, eliminates the top half, and then found a dog. So it works for strings as well. So yeah, pretty happy with this algorithm, I have to say. Heck yeah, so that's binary search in a nutshell. Takeaways. So even though we wouldn't use that probably in the real world, I wouldn't use that in like a production environment. I would probably use something like a regular for loop or an array for each loop instead, because maximizing brain cycles versus computer cycles is usually a better trade-off. I can get stuff done faster, more efficiently, and human efficiency oftentimes is more important than computer efficiency, just kind of the way that it works in the real world. So, but this was a super fun and an interesting exercise, and a way for me to like get that into my brain of how binary search works, because I learned stuff by very hands-on, by doing, and so that was a way for me to like kind of grasp how this thing works on a deep level. So yeah, if you like stuff like this, exploring interesting new concepts of computer science, development, programming, building stuff, I love this stuff. I'm going to be coming back with some more videos in the future, some tutorials, live coding, and if you have any ideas or suggestions, please hit me up in the comment section. And if you found this helpful and want to like help other people to find this sort of content, you know what to do. I think that's going to do it for me. My name's Don Juan. Keep coding, keep building awesome things, and I'll catch you in the next video. Take care.